In this video, I want to give you a sense of how the whole memory hierarchy works together to support the execution of a program, and to explore the connections between the different views of memory that we've seen, including the perspective of the C program, the assembly code, the hardware, and the operating system. We'll do this by analyzing a small snippet of C code, this function that clears the contents of an array, setting them all to 0. If we think about the perspective of the C program, we can draw a stack diagram to keep track of what's going on in memory. When this function is called, we know that the caller's stack frame is on top of the stack, and then we add a new stack frame for this function. In that stack frame, we will have all of the local variables of the function, including the arguments, the array pointer, and the size integer, as well as our loop variable I. If the pointer that was passed in refers to a dynamically allocated array on the heap of size 8, then at the start of the function, the stack frame will look like this. The pointer is storing the address where the chunk of memory begins, and the variable size is storing an integer. Then, as we enter the loop, we initialize the variable I to 0. And then on the first iteration of the loop, we will calculate the pointer R plus I. And since I is 0, that will refer to the address of index 0 in the array. And then we follow that pointer and put the value 0 into that location. On the next iteration, when I is 1, R plus 1, thanks to pointer arithmetic, will evaluate to the address where index 1 of the array is stored, and then following that pointer, we put a 0 at that location. And so when we're reasoning about the C code directly, this abstract stack and heap diagram representation is a logical way to keep track of what's going on. But we know that our C code gets compiled into assembly, and the binary representation of the assembly instructions are what's actually in memory and actually being executed by the CPU. So we can also reason about this program from the perspective of the assembly code. When we arrive at the first instruction in the body of this function, we know that the base pointer has already been set up to refer to the bottom of the stack frame, and the instruction pointer should store the address of the instruction we're about to execute. In addition, the process of calling the function put the arguments onto the stack, and they appear just below the base pointer. So at the locations 8 and 12 below the base pointer, we have the values for the variables size and the array pointer. As we step through the assembly code, the instruction pointer increments each time, and we'll also be moving data between memory and registers. Initially, we retrieve a value from the memory location base pointer plus 8, and that's the size, into the EAX register. Then we are moving the value 0 into the location above the base pointer, and this corresponds to initializing the variable I to 0. Then we execute this jump instruction, which loads the address ending in A4 into the instruction pointer, meaning that the next instruction we will execute is this compare. We're comparing the value in EAX, which is 8, with the value in the memory location base pointer minus 4, which, recall, is where we stored I. And since 0 is less than 8, we will jump, putting the address ending in 8b into the instruction pointer, and making this move the next instruction that we will execute. But what we've just done is check the loop condition, and now we're at the top of the loop body. So these instructions should correspond to adding I to the pointer, and then following that pointer and putting a 0 in the corresponding location. We first retrieve base pointer plus 12 into the ECX register, So the register now contains the address where the array begins, and we're retrieving the value of I into the EDX register. The next instruction, LEA for load effective address, is one that comes up a lot in pointer arithmetic and array indexing. It's used to calculate memory addresses. Specifically here, we have the ECX register as the base, and the EDX register as an offset, and the size of our offset is 4. The reason it's 4 is because an integer takes up 4 bytes of memory, and we're working with an integer array. But right now, since EDX is 0, there is no offset being calculated, and so we just get the value of ECX, and we're storing that back into the ECX register. Then we are moving the value 0 into the memory location given by the ECX register, which corresponds to following a pointer and putting the value 0 in memory. In this case, that will put the value 0 into this memory location. Now we add 1 to the location where we're storing I, which corresponds to our loop update, and then we're back to the instructions that check the loop condition. We'll compare the EAX value 8 to the value of I, which is 1, and since I is less, we'll jump back to the top of the loop. We start by again retrieving the array pointer into ECX, which on this iteration makes no change. But then we retrieve the value of I into EDX. And since I has been updated, now we're retrieving the value 1. Now when we perform this load effective address, we are using the value from EDX as an index, and the 4 tells us the size of the data type. So we will add 1 times 4 to our base value in the ECX register. And so this instruction will end up adding 4 to the value of ECX. Which means that on the next instruction, when we put a 0 into the memory location specified by ECX, we are now putting a 0 at the location ending with A4, which corresponds to following the pointer r+1 and putting a 0 in that memory location. Subsequent iterations of the loop proceed similarly, and will fill in zeros to the next several memory locations in the heap segment. Each time we will retrieve the initial value of the pointer and the current value of I, and then we will compute the offset to tell us where to put the value 0. So within this assembly code, we can identify a number of memory reads and writes, where for some of these operations we are retrieving a value from memory into a register, and for others we are putting a value into a memory location. And in some cases, like where we're incrementing I, we are both retrieving its current value and writing the updated value back. But all of this so far, whether we were thinking about the C code or the assembly, has been from the idealized perspective of the virtual memory abstraction. We know that our program doesn't actually get to decide exactly where in the RAM its data goes, and often when it's accessing its data, it won't actually be retrieving it from the RAM, it will find the data that it's looking for already in the CPU cache. So let's think about what's going on when we perform these various memory operations in terms of the whole memory hierarchy. I've illustrated here an abstract representation of a 4-core CPU, and for each of these CPU cores, we have level 1 and level 2 caches, and all 4 of the cores share a level 3 cache as well as the system's main memory. When we run our program, it will be executing on one of the CPU cores, as chosen by the operating system's scheduler. Let's suppose we're running on this one. As this CPU core is executing our program, we know that it is performing fetch, decode, and execute on each of the instructions. And so we know that the assembled binary representation of these instructions lives in the program's memory at these virtual addresses, but we also know that virtual addresses get translated via the page table into physical addresses. So somewhere in the computer's main memory, these instructions will be stored, but which actual frame they are placed in is decided by the operating system, and then the operating system will keep track in the page table of where that page of memory was placed. In this diagram of main memory, I have illustrated that some portion of memory is storing data belonging to the operating system, and some portion of the operating system's data includes the page table for this process. And in that page table, we should have an entry for the page that all of these instructions are on. To figure out what sorts of mappings the page table stores, we need to figure out what portion of this virtual address constitutes a page number and what portion constitutes an offset. I've listed here fairly typical parameters for a modern desktop system, and if the system uses a page size of 4K bytes, then we will have 2 to the 12 bytes on each page, which means that the last 12 bits of a virtual address constitutes the offset. Looking at these hex addresses, 12 bits corresponds to 3 hex digits, which means that the last 3 digits are the offset within the page, and therefore the first 5 hex digits are the page number. And conveniently, all of these instruction addresses have the same first 5 digits, so they are all on the same page of memory, and so the page table must contain some mapping for that page telling us which frame of physical memory that's actually located in. The frames of physical memory will be indexed based on the size of the RAM, and in this case the computer has 8 gigabytes of main memory, which is 2 to the 34 bytes. And so we have 2 to the 34 bytes, and therefore 34-bit virtual addresses. But since 12 of those bits are an offset, that means that we have 22 bits specifying the frame number. Of note, since I'm using IA32 for the assembly, the program's virtual address space is only 2 to the 32 addresses, and we have 4 times that much physical memory. But that's entirely okay, because the operating system can keep track in the page table and map our 32-bit virtual addresses into 34-bit physical addresses. The same thing happens in the other direction when we use x86-64 assembly, which typically has 48-bit virtual addresses, and those 48-bit virtual addresses become 36-bit page numbers, but the page table could map a 36-bit page number to a 22-bit frame number perfectly fine. In order to execute these instructions, we have to fetch them, which means that every step of the program is reading an instruction from this page of memory. But of course, when we're reading nearby things in memory, we should expect that the cache is helping out, and that we're not always having to go all the way to main memory. And so we should expect that as we are stepping through these instructions, in fact, they have been loaded into the various levels of the cache, and so there should be a block of memory containing these instructions in each of the levels of the cache. Of note, in my diagram, as is typical on modern systems, the level 1 cache is split into a data cache and an instruction cache. And so, When we are executing these instructions, we should expect that the block containing nearby instructions is present in the level 1 instruction cache. We're not going to go into any further depth on instruction caching. We've been focusing primarily on data caching, but it's important to note that every time we fetch an instruction, we are reading from memory, and the cache is helping to accelerate those reads just like it's helping us accelerate accesses to our data. So now let's dive deep on how the memory hierarchy is interacting when we read and write data. When we perform an instruction that reads or writes, we know that our process is interacting with the memory hierarchy. And in fact, when we issue a read request, the CPU core will send that request simultaneously to many levels of the hierarchy. On this instruction, we are trying to read from an address in our virtual address space. So the processor will take the value in the base pointer register, add 8 to it, and then send that address to the different places where it might find the data. That means that this address is going to the level 1 data cache, the level 2 cache, and the level 3 cache all at once. In addition, that address is being sent to the TLB, which stands for Translation Look-Aside Buffer. The TLB is a special purpose bit of cache whose job is to accelerate address translation. Because the addresses that appear in our assembly code and show up in the registers are actually virtual addresses, in the event that we need a physical address to retrieve the data from main memory, we're going to have to look up the page number in the page table. But if the page table is stored in physical memory, that lookup is slow. And so the translation look-aside buffer is caching page-to-frame translations so that we can accelerate the process of translating between a virtual address and a physical address. And in fact, it's possible that some levels of the cache, especially the lower levels, might themselves be physically indexed, meaning that the index and tag we are using are based on physical addresses rather than virtual addresses. And so the TLB allows us to translate from a virtual address to a physical address and find our data in a physically addressed cache without requiring an intermediate step that would go to RAM in order to perform the translation. Again, we're not going to dive deep into the functioning of the TLB, but it's good to know that it's there and that some levels of cache can be physically addressed. For the remainder of this video, we're going to focus on the level 1 data cache, but we should remember that when the CPU core is looking for data in its level 1 cache, it's simultaneously requesting the same data from other levels of cache, and after it gets the translation from the TLB, it could be requesting the same data from RAM as well. And by simultaneously sending these requests to many levels of the hierarchy, the CPU can proceed as soon as it gets back an answer from any of them. If the data happens to be in the level 1 cache, it can then just cancel the requests to the L2 and L3 caches and carry on executing the instruction. By sending all of these requests simultaneously, we get the data back as soon as possible from wherever it happens to be, but it also has the advantage that the other levels of cache will have received a request for the data, and so even if they end up not needing to send a reply, they can mark that data as recently used, which is helpful in keeping track of what data should we keep around when we have to evict something. So now, to zoom in on the level 1 data cache, let's think about a few more parameters of our typical system. First of all, we have 64-byte cache lines, and since 64 is 2 to the 6th, we know that we have the last 6 bits of the address serving as an offset within the block of data. And we have a level 1 cache that stores 2 to the 15th bytes of data and is 8-way set associative. Since it's 8-way set associative, that means that for each index in this cache, there are 8 lines, and so any block of data with that index could potentially go in any of the 8 lines within the set. When we combine these pieces of information, that we have 2 to the 15th bytes and 2 to the 6th bytes constitute one block, that means that there must be 2 to the 9th lines in the level 1 cache. And since those lines are grouped into sets of 8, or 2 to the 3rd, we know that we have 2 to the 6th different sets in the L1 cache. And since there are 2 to the 6th sets, that means that we have 6 bits specifying the index in the L1 cache. We could likewise determine that we have 6 index bits in the level 1 instruction cache, and by a similar calculation, we could determine that the level 2 cache has 9 index bits, because the block size is the same for all of the cache levels. And for the level 3 cache, since that has 16-way associativity, we end up with 12 index bits. But since we're focusing on the level 1 cache, let's think about how our virtual addresses get split into tag, index, and offset based on these values. The first memory address from which our program reads data is base pointer plus 8. So let's calculate that address and translate the hex into binary, and then split it into tag, index, and offset. The base pointer stores this address ending in 78, and when we add 8 to that, in hexadecimal we end up carrying the 1 and getting the address ending with 80. When we translate the hexadecimal into binary, we get this 32-bit value, and then using the offset and index sizes that we calculated, we know that the last 6 bits will be an offset within the block, and the next 6 bits will be the index into the level 1 cache. And what remains, these high order 20 bits, constitute the tag. So now that we know the index is 111110, we know that if the data is in the level 1 cache, it will be somewhere in set 111110. And within this set, there are 8 lines, and so we need to check whether any of those 8 lines have both a matching tag and a valid bit set to 1. Here, since writing 20 bits of binary is tedious, I have represented the tag in hex, and we have a matching tag that is valid. This makes sense because before calling this function, we pushed the arguments onto the stack, and so these locations in memory were recently written. And so it makes sense that once we start executing the function, we find those recently written locations still in the cache. Now that we've identified that the block of data we're looking for is in the cache, we can use the offset to determine where within these 64 bytes is the thing that we're actually trying to read. And since the offset is all zeros, that means that within these 64 bytes of data, the thing we're looking for starts at the 0th address. And so we retrieve this value 8 into the EAX register. We found our data in the level 1 cache, and so we have a cache hit, and the program proceeds without having to wait for any of the lower levels of the hierarchy to respond. On this next instruction, we are writing data to memory, but again, we can determine the address and split it up into tag, index, and offset. And this time, when we subtract 4 from the base pointer, we get an address ending with 74. And since the last 2 hex digits have changed, that will update the last 8 binary digits. And the result is that we now have a different index. We crossed over the boundary between one cache block and another when we went from this location to this one. So now we're looking for index 111101, which corresponds to a different set in the cache. And so we look at that set and check whether any of the 8 lines within that set have a matching tag and are valid. And again, we find the tag that we're looking for in a valid cache line. And so we know that the data we're looking for is already in the level 1 cache, which again makes sense because before executing the body of the function, we know we must have pushed the instruction pointer and then the old base pointer. And so these 2 locations here must have been recently written, and they are within the same cache block. So now we are writing the value 0 into this location, and we need to determine what index within that chunk of memory are we referring to. And within this 64-byte block, if we're thinking about moving integers or other 32-bit values around, 32 bits is 4 bytes, and so this block contains 16 32-bit values, numbered 0 through 15, and we are currently writing number 13. So we have 15, 14, 13. We are looking at the third to last 32-bit value within this cache block, and we are writing the value 0 to that location within the line. Since we wrote to that line of the cache, we need to make sure that the line of cache is marked as dirty, and it already is because of those previous writes. But this means that later, if we end up evicting this line from the cache, that we will have to save this block of data that we know has been updated into the lower levels of the memory hierarchy because the one in the level 1 cache is more up to date than the lower levels, thanks to our cache hit on this and other writes. Our next few operations perform reads on the variable I and the array pointer, so we are hitting these same locations again. But when we get down to our write operation, that is storing a 0 into the heap array, we're now accessing a very different virtual address. As of the first time through this loop, when we get to this write operation, the ECX register is storing the address here ending in A0. And so we should do the same translation on that virtual address. When we translate this address, we get an index of 000110, corresponding to this set in the cache. And now it's entirely plausible that if this array hasn't been accessed in a while, none of that data is presently in the cache. To check whether it is in the cache, we need to check all 8 tags in this set, and if any of those 8 tags match with this one and are valid, then we will have found the data, but let's suppose that none of them match. In that case, we will have a cache miss, and we will have to wait for a response from lower levels of the memory hierarchy. It might be that we get a hit in the L2 cache or the L3 cache, but let's suppose that those both miss, and actually that the TLB also misses, so we haven't even translated this address recently. In that case, we will need help from the operating system to look up in the page table where is this virtual address stored in physical memory. Conveniently, we have the coincidence that this line we've already drawn separates the 12 bits of page offset from the 20 bits of page number. So our page number in hex is 0804D, and we can look up that page number in the page table. And the page table tells us that that's located at physical address 253DD8A5. And so at that location in the physical memory is a frame where that frame contains the page of data starting at address 0804D offset 000 and contains offsets all the way up to FFF. So this 4 kilobyte page of data contains the particular data that we were looking for. So now that we have a frame number from the page table, we can replace our page number with that frame number and combine it with the page offset as the address that we are sending to the RAM. And the RAM will send back data that came from within this page, and in fact, it will send us a 64-byte block of data that we can use to fill in a line of the cache. Now that we're bringing new data into the cache, we need to use our cache replacement policy to decide among the 8 lines in this set which one is going to be replaced. And we know that if any of those lines are invalid, those should be replaced first. But if all 8 lines in the set are valid, then it will be based on recency, which thing we kick out. Unfortunately, if we have greater than 2-way associativity, it's not practical to keep track of exact least recently used data. In particular, if we were trying to keep track of the exact order in which these 8 things had been used, then every time we access any line, we would have to reshuffle all of the LRU bits for everything in this set. So instead, various approximations to LRU are used in practice. One approximation that's common in this sort of 8-way set associative cache is to have 3 LRU bits, where the first bit refers to which was least recently used between the top and bottom halves of the set, and then the second bit is within the pairs for that half, and then the last bit is which line within the pair was least recently used. So supposing that our replacement policy ended up putting the block of data into this line of the set, then we would fill in the tag metadata with the bits of our tag from the virtual address, and we mark that line of the cache as valid. And now we can set our LRU bits based on this. Since we just accessed this line of the cache, it is the most recently used, and so it should have all 3 LRU bits set to 0. Meanwhile, the top half of this set was more recently used than the bottom half, so the top half should all have its first bit set to 0. And within this top half, the bottom pair was more recently used, so this line should have its second bit set to 0. Likewise, we know that the bottom half should all have its first bit set to 1. The top pair in the top half should have its second bit set to 1. And this bit here should also be 1 because within the pair, that line was least recently used. And so all of these are things that can be set based on just this one access, and we don't alter these other bits that I have left blank, and they will still convey information about within the other portions of the set which things are least recently used. But of note, this doesn't give us exact least recently used information. It might be that next time we go to kick something out, we would prefer to kick out something in the bottom half, when in fact this line here just got lucky in being next to the line that we accessed most recently, and it was in fact the oldest. So when we have non-trivial associativity, we end up doing some approximation of least recently used. And in fact, the page table also does an approximation of least recently used. But since physical memory is fully associative, even this approximation would be way too much to keep track of. And so the operating system tends to use something more like a flag or a counter for has this thing been recently used at all, and that will get periodically reset. But importantly, each of these are doing some sort of approximation of least recently used that will generally make it so that data we are accessing a lot gets kept in the higher levels of the hierarchy. But all this was just messing with the cache metadata. The actual point here was to bring a block of data from the RAM into the cache, and then to update one of the entries in that block to be 0. Which entry are we actually setting to 0? Well, that depends on the offset within the block, and here we have an offset of 32 within our 64-byte block. So somewhere in the middle of that block of data, we are writing the value 0. And now, even though we just brought the block into the cache, because we have updated part of that block, we know that this block is more up to date than what's at the lower levels of the hierarchy, and so in the metadata we should mark it as dirty. As we proceed through executing our program, we will frequently be reading this pointer into a register, and we will be both reading and writing this location where we're storing the variable I, and as we tick forward through the entries in the array, and correspondingly the virtual memory locations in the heap segment, the next few of those locations will be within this same block of data. But of course, if the size is large enough, then we will eventually run out the end of this block, and we will need to retrieve a new block with a new index from a lower level of the hierarchy into the level 1 cache. Of course, all of this translation is also happening for the other levels of the cache, because we know that each level of the cache is typically storing a subset of the data at the next level down, which means that when we brought a block of data from RAM into the level 1 cache, we probably also brought that block into the level 2 and level 3 caches. And so all of this work going on behind the scenes ensures that as we step through our array, the data that we are looking for is likely to be quickly accessible. So the takeaways here are that our C code and the assembly have a virtual memory perspective where they see addresses that correspond to their virtual address space, but behind the scenes there is translation going on to determine where in physical memory is that stored. But also the memory accesses are being accelerated through the use of caching, and some levels of the cache may use the virtual addresses from the program directly, whereas other levels of the cache might use the physical addresses based on the operating system's translation. Whenever a process is trying to access data, it's sending the read or write request to many levels of the hierarchy simultaneously, and as soon as it gets a response back from any level of cache, it can proceed with its execution. But behind the scenes, a lot of work is going on to split up these addresses to locate the data within the cache, and to make sure that the data we are likely to use in the near future is kept as close as possible to the CPU core where it's going to be needed.